Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
Aurel Stodola stands as a monumental figure in the history of mechanical engineering, particularly celebrated for his transformative contributions to steam turbine technology. His rigorous analytical approach, coupled with a deep understanding of thermodynamics and mechanics, enabled him to tackle some of the most pressing challenges facing early turbine designs. Among these challenges, the problem of blade vibration and subsequent failure held particular significance. Turbine blades, subjected to intense centrifugal forces and high-velocity steam flows, were prone to resonance, leading to catastrophic structural damage. Stodola's innovative methods for analyzing blade vibration frequencies proved instrumental in mitigating these risks and paving the way for more reliable and efficient turbine operation. The imperative to improve turbine blade design arose directly from the limitations of early steam turbine technology. Initial designs, often based on empirical observations and trial-and-error approaches, suffered from frequent blade failures. These failures resulted in costly repairs, reduced operational efficiency, and, in some cases, dangerous accidents. The need for a more systematic and predictive approach to blade design became increasingly apparent as turbines grew in size and complexity. Stodola's work addressed this need head-on, providing engineers with the tools necessary to analyze blade vibration characteristics and avoid resonance conditions. Stodola's most notable contribution in this area is the development of what is known as the Stodola ellipse, or Stodola's method. This method provides a graphical and analytical framework for determining the natural frequencies of turbine blades. At its core, the method involves solving a differential equation that governs the vibration of a beam representing the turbine blade. The equation considers factors such as the blade's geometry, material properties, and the centrifugal forces acting upon it. Stodola ingeniously transformed this complex differential equation into a more manageable form amenable to graphical solution. The essence of Stodola's method lies in iteratively refining an initial guess for the blade's deflection curve. By repeatedly calculating the blade's deflection based on the assumed frequency, and then using this calculated deflection to improve the frequency estimate, the method converges towards the true natural frequencies of the blade. This iterative process can be visualized graphically, with each iteration represented as an ellipse on a plot of frequency versus deflection. The intersection of these ellipses provides an accurate estimate of the blade's natural frequencies. The mathematical foundation of Stodola's method rests upon the principles of beam bending theory and the theory of vibrations. The differential equation governing the blade's vibration can be derived from Euler-Bernoulli beam theory, which relates the blade's deflection to the applied forces and moments. The solution of this equation yields the blade's mode shapes, which describe the pattern of deformation at each natural frequency. Stodola's innovation was to develop an efficient iterative procedure for solving this equation, making it practical for engineering applications. A tangible example of Stodola's work can be found in his contributions to the design of early Brown Boveri turbines. Brown Boveri, a Swiss engineering company, was a pioneer in the development of steam turbine technology. Stodola collaborated closely with Brown Boveri engineers, applying his methods to optimize the design of their turbine blades. His analyses helped to identify and eliminate resonance problems, leading to more reliable and efficient turbine operation. The improved designs directly translated into reduced downtime and enhanced power generation capacity for Brown Boveri's clients. The impact of Stodola's work extended far beyond Brown Boveri. His methods were widely adopted by turbine manufacturers around the world, becoming a standard tool for blade design and analysis. Engineers used Stodola's method to predict and prevent blade failures in a wide range of turbine applications, from power generation to marine propulsion. The method's simplicity and accuracy made it accessible to engineers with varying levels of mathematical expertise. Stodola's initial research was significantly influenced by the work of William John Macquorn Rankine, a Scottish engineer and physicist. Rankine's contributions to thermodynamics, particularly his work on the steam engine cycle, provided a crucial foundation for Stodola's subsequent investigations. Rankine's thermodynamic cycle analysis allowed Stodola to understand the energy transfer processes within steam turbines, enabling him to optimize turbine designs for maximum efficiency. Furthermore, Rankine's focus on the practical application of scientific principles resonated deeply with Stodola's own engineering philosophy. The reception of Stodola's work was overwhelmingly positive. Engineers and scientists recognized the practical value of his methods and their ability to solve real-world problems. His publications, including his seminal book Steam Turbines became standard references for turbine design. While Stodola's method was widely praised for its accuracy and efficiency, it also faced some critiques. Some researchers argued that the method was too simplistic and did not adequately account for certain factors, such as the effects of damping and aerodynamic forces. This led to the development of more sophisticated numerical methods, such as finite element analysis, which could provide more detailed and accurate predictions of blade vibration behavior. However, Stodola's method remained a valuable tool for preliminary design and quick assessment of blade vibration characteristics. Stodola's work on turbine blade vibration directly influenced later turbine designers at Brown Boveri and other firms. His methods became an integral part of their design process, ensuring the reliability and efficiency of their turbines. Specific individuals who benefited from Stodola's work include his students and collaborators, who went on to make significant contributions to turbine technology. These engineers built upon Stodola's foundation, developing new and improved methods for turbine design and analysis. The legacy of Stodola's work continues to be felt in the design of modern steam turbines, which owe their efficiency and reliability in substantial measure to his pioneering contributions. His influence extends even to the design of gas turbines, although his initial focus centered on steam-driven systems. While his later work encompassed broader areas, his early investigations into steam turbines laid the groundwork for much of what followed. Aurel Stodola's deep understanding of vibration characteristics, particularly within turbine blades, naturally extended into the broader realm of rotor dynamics. He addressed the critical problem of shaft whirling and vibration in rotating machinery, a phenomenon that, if unchecked, can lead to catastrophic failures. His work provided crucial insights into the behavior of rotating shafts and established methods for calculating critical speeds, the speeds at which resonance occurs and vibrations become dangerously amplified. Stodola's approach to determining critical speeds was multifaceted. He skillfully employed Rayleigh's method, rooted in energy principles, to approximate these crucial values. Rayleigh's method, in essence, posits that the frequency of vibration of a system can be accurately estimated by considering the maximum potential and kinetic energies of the system during its oscillation. Stodola masterfully applied this principle to rotating shafts, considering the potential energy stored in the shaft's elasticity and the kinetic energy of the rotating mass. By equating these energies, he derived an equation that allowed for the approximate calculation of the critical speed. This method proved particularly valuable for complex rotor geometries, where exact analytical solutions were elusive. In addition to Rayleigh's method, Stodola developed other approximation techniques tailored to specific rotor configurations. His work explored the behavior of diverse rotor types, including those found in steam turbines and electrical generators. He recognized that the geometry of the rotor, the distribution of mass along the shaft, and the elasticity of the shaft material all played significant roles in determining the critical speeds. His methods allowed engineers to account for these factors in their designs, ensuring that the operating speeds of the machinery were sufficiently far from the critical speeds to avoid resonance. A tangible illustration of Stodola's work can be found in his analysis of turbine rotors. These rotors, typically composed of numerous blades attached to a central shaft, present a complex dynamic system. Stodola developed methods to determine the natural frequencies of these rotors and to predict their response to various operating conditions. He considered the effects of centrifugal forces, steam pressure, and other factors that could influence the rotor's vibration characteristics. His analysis enabled designers to optimize the rotor's geometry and material properties to minimize vibration and enhance its reliability. Stodola also addressed the practical problem of balancing rotating machinery. Even with careful design and manufacturing, rotors often exhibit some degree of imbalance, which can generate significant vibrations during operation. Stodola championed dynamic balancing, a technique that involves measuring the vibrations of the rotor while it is rotating and then adding or removing mass at specific locations to counteract the imbalance. This process requires sophisticated instrumentation and careful analysis, but it can significantly reduce vibration levels and extend the lifespan of the machinery. His seminal book, Steam and Gas Turbines, detailed this comprehensive approach to rotor dynamics and balancing. This book became a cornerstone reference for engineers involved in the design and operation of rotating machinery. It presented a clear and rigorous treatment of the underlying theory, along with practical guidance on how to apply the theory to real-world problems. The book's enduring influence is a testament to Stodola's profound understanding of the subject and his ability to communicate complex ideas in an accessible manner. Stodola's work built upon the earlier contributions of August Ferpel, a German engineer renowned for his work on elasticity and vibration. Ferpel's research provided a foundation for understanding the behavior of elastic bodies under stress, which was essential for Stodola's analysis of rotating shafts. Ferpel's work on the theory of elasticity, particularly his methods for calculating stresses and strains in beams and plates, provided Stodola with the tools he needed to analyze the deformation of rotating shafts under centrifugal forces. The influence of Ferpel's work is evident in Stodola's reliance on energy methods and his careful consideration of the material properties of the shaft. Stodola's contributions to rotor dynamics had a profound impact on later researchers in the field. His work directly influenced engineers such as Mario Prol, who developed the transfer matrix method for analyzing the vibration of rotating shafts. Prol's method, which involves dividing the shaft into a series of discrete elements and then relating the motion of each element to its neighbors, provided a more efficient and accurate way to calculate critical speeds. Prol's work was a direct extension of Stodola's approach, building upon his fundamental principles and extending them to more complex rotor systems. Another engineer significantly influenced by Stodola was Henry Jeffcott, who developed a simplified model for analyzing the vibration of a flexible rotor. Jeffcott's model, which treats the rotor as a single mass supported by a flexible shaft, provided a valuable tool for understanding the basic behavior of rotating machinery. While Jeffcott's model was simpler than Stodola's more comprehensive approach, it captured the essential physics of the problem and provided a useful framework for design and analysis. Jeffcott explicitly acknowledged Stodola's work as a major source of inspiration for his own research. The impact of Stodola's work is evident in the continued use of his methods for analyzing and balancing rotating machinery. While modern finite element methods offer even greater precision and flexibility, Stodola's fundamental principles remain relevant and provide a valuable foundation for understanding the behavior of complex rotor systems. His legacy continues to inspire engineers to develop new and improved methods for ensuring the reliability and efficiency of rotating machinery. His contributions are testament to his deep understanding of the underlying physics and his ability to translate that understanding into practical engineering solutions. His book remains a vital resource for those seeking a thorough grounding in the principles of rotor dynamics. Stodola's inventive spirit and analytical prowess extended far beyond steam turbines and rotor dynamics, leading him to make significant contributions to the understanding and development of gas turbines. The challenge of achieving efficient combustion and reliable high-temperature operation in these machines presented a formidable engineering hurdle at the time. Stodola's work addressed these issues with characteristic rigor and insight. The genesis of Stodola's interest in gas turbines can be traced to the limitations he perceived in existing steam turbine technology. While steam turbines had achieved considerable success, their efficiency was fundamentally constrained by the properties of water as a working fluid. Gas turbines, with their potential for higher operating temperatures and simpler cycles, offered a pathway to improved thermodynamic performance. Stodola's approach to gas turbine analysis was rooted in the principles of thermodynamics, heavily influenced by the foundational work of Sadi Carnot. Carnot's conceptualization of the ideal heat engine operating on the Carnot cycle provided a benchmark against which the performance of real-world engines could be assessed. Stodola applied these principles to analyze the gas turbine cycle, considering the effects of pressure ratio, temperature, and component efficiencies on overall performance. His analysis provided a framework for optimizing the design of gas turbines and identifying areas for improvement. Specifically, Stodola meticulously examined the impact of pressure ratio on the thermal efficiency of the gas turbine cycle. He demonstrated that increasing the pressure ratio could lead to higher efficiencies, but only up to a certain point. Beyond this optimal value, the benefits of increased pressure were offset by increased compressor work and other losses. Stodola's analysis provided engineers with a valuable tool for selecting the appropriate pressure ratio for a given gas turbine application. Furthermore, Stodola investigated the influence of turbine inlet temperature on gas turbine performance. He recognized that higher temperatures could lead to improved efficiencies, but also pose significant challenges for materials and component design. Stodola's work highlighted the importance of developing high-temperature materials and cooling techniques to enable the operation of gas turbines at their full potential. Stodola's thermodynamic analysis of gas turbine cycles was complemented by his experimental work on gas turbine components. He conducted extensive tests on compressors, turbines, and combustion chambers to validate his theoretical predictions and gain a deeper understanding of the underlying physical phenomena. These experiments provided valuable data for improving the design and performance of gas turbine components. For example, Stodola's research on compressors focused on understanding the complex flow patterns within these machines and minimizing losses due to friction and turbulence. He developed new methods for measuring the velocity and pressure distribution within compressors, providing insights into the factors that limited their efficiency. This work led to improvements in compressor blade design and overall compressor performance. Similarly, Stodola's investigations of turbine performance involved detailed measurements of the flow field within turbine stages. He studied the effects of blade geometry, nozzle design, and operating conditions and turbine efficiency. His research contributed to the development of improved turbine blade profiles and optimized turbine stage designs. Stodola also made significant contributions to the understanding of heat transfer and fluid flow in turbomachinery. He recognized that these phenomena played a crucial role in determining the performance and reliability of gas turbines. Stodola developed analytical models and experimental techniques for studying heat transfer and fluid flow in complex geometries, providing engineers with the tools they needed to design more efficient and durable gas turbine components. The publication of Stodola's book, Steam and Gas Turbines, served as a comprehensive resource for engineers working on gas turbine development. The book presented a detailed account of Stodola's theoretical and experimental work, providing a valuable foundation for the design and analysis of gas turbines. The book became a primary reference for gas turbine engineers around the world, shaping the development of the field for decades to come. Stodola's work on gas turbines had a profound influence on later gas turbine engineers, including pioneers such as Sir Frank Will and Hans von Ohain. Both Will and von Ohain explicitly acknowledged Stodola's book as a major source of inspiration for their own research. Will, in particular, drew heavily on Stodola's thermodynamic analysis of gas turbine cycles in his development of the first jet engine. Von Ohain, similarly, found Stodola's work invaluable in his design of the first operational turbojet engine. The impact of Stodola's contributions to gas turbine technology is evident in the widespread use of gas turbines in a variety of applications, including power generation, aviation, and industrial processes. Modern gas turbines owe much to Stodola's pioneering work, which laid the foundation for the development of these powerful and efficient machines. His legacy continues to inspire engineers to push the boundaries of gas turbine technology and develop new and improved designs. His meticulous approach to thermodynamic analysis, combined with his dedication to experimental validation, established a standard of excellence that continues to guide gas turbine research and development. The principles he elucidated regarding pressure ratio optimization, temperature effects, and component efficiencies remain fundamental to gas turbine design. His influence extends to the development of advanced cooling techniques and high-temperature materials, which are essential for achieving the high efficiencies demanded of modern gas turbines. The success of Whittle and von Ohain in developing the first jet engines to be directly attributed in part to the solid foundation provided by Stodola's work. They were able to build upon his theoretical framework and experimental findings to overcome the many technical challenges involved in creating a practical jet engine. Stodola's book served as a vital guide, providing them with the knowledge and insights they needed to succeed. Stodola's influence also extended to the development of combined cycle power plants, which utilize gas turbines in conjunction with steam turbines to achieve higher overall efficiencies. His work on both gas and steam turbines provided a unique perspective on the integration of these technologies, leading to the development of highly efficient power generation systems. These systems now play a critical role in meeting the world's growing energy demands. While modern computational fluid dynamics simulations offer unprecedented levels of detail in analyzing turbomachinery flows, Stodola's fundamental thermodynamic analysis remains a valuable tool for understanding the overall performance of gas turbines and optimizing their design. His work provides a crucial link between theory and practice, enabling engineers to make informed decisions about gas turbine design and operation. As the 20th century progressed, Aurel Stodola's intellectual curiosity expanded beyond the immediate practicalities of turbine design and thermodynamics. He began to grapple with the broader implications of technology, particularly the integration of human judgment and control within increasingly complex engineering systems. This led him to explore the nascent field of technical cybernetics, a precursor to modern cybernetics and control theory. Stodola recognized that engineering systems were evolving to a point where purely mechanistic approaches were insufficient. The operator, the human element, needed to be considered as an integral part of the system's overall function. This was a radical departure from the traditional view of the engineer as a detached designer, separate from the operational realities of the machines they created. Stodola's perspective was shaped by the increasing automation of industrial processes and the growing complexity of power generation and distribution networks. He observed that the performance of these systems depended heavily on the skill and judgment of human operators who were responsible for monitoring, adjusting, and intervening in response to unforeseen events. He saw the need for a more systematic approach to understanding and optimizing the interaction between humans and machines, a field that would later be formalized as human factors engineering. One of Stodola's key contributions to this area was his emphasis on the use of thought experiments, or jet intent experiment, in engineering design and problem solving. drawing inspiration from the work of physicists like Albert Einstein, who famously used thought experiments to develop the theory of relativity. Stodola argued that engineers could use mental simulations to explore the behavior of complex systems under different conditions. This approach allowed engineers to anticipate potential problems, evaluate design alternatives, and optimize system performance before committing to expensive physical prototypes. Stodola's application of thought experiments in engineering was deeply rooted in his understanding of thermodynamics and fluid mechanics. He recognized that these disciplines were based on idealized models and assumptions, and that real-world systems often deviated from these idealizations. By using thought experiments, engineers could explore the consequences of these deviations and develop more robust designs that were less sensitive to uncertainties and variations. For example, in designing a new steam turbine, Stodola might have used a thought experiment to explore the effects of variations in steam pressure and temperature on the turbine's efficiency. By mentally simulating the flow of steam through the turbine under different conditions, he could identify potential bottlenecks or inefficiencies and adjust the design accordingly. This approach allowed him to optimize the turbine's performance over a wide range of operating conditions. Stodola's interest in the philosophical implications of technology led him to write extensively on the subject. His book, Thoughts on Technology and the Future, explored the impact of technology on society, culture, and the human condition. In this work, Stodola argued that technology was a powerful force that could be used for either good or ill, and that it was the responsibility of engineers to ensure that technology was used in a way that benefited humanity. Stodola's philosophical views were heavily influenced by the positivism and pragmatism of Ernst Mach. Mach, an Austrian physicist and philosopher, argued that scientific knowledge should be based solely on empirical observations and that theoretical concepts should be judged by their practical usefulness. Stodola adopted a similar approach in his own work, emphasizing the importance of experimental validation and the practical application of theoretical knowledge. This emphasis on practicality is evident in Stodola's approach to engineering design. He believed that engineering should be driven by the needs of society and that engineers should strive to create technologies that were both efficient and sustainable. He was deeply concerned about the environmental impact of industrialization and advocated for the development of cleaner and more efficient energy technologies. Stodola's influence on the development of technical cybernetics can be seen in the work of later researchers who explore the integration of human and machine intelligence. Norbert Wiener, the founder of cybernetics, explicitly acknowledged Stodola's contributions to this field. Wiener's work on feedback control systems and the communication of information between humans and machines built upon Stodola's earlier insights into the importance of human factors in engineering design. Furthermore, Stodola's emphasis on thought experiments in engineering has had a lasting impact on engineering education and practice. Many engineering schools now incorporate thought experiments into their curricula, teaching students to use mental simulations to solve complex problems and develop innovative designs. This approach helps students to develop their intuition and creativity, enabling them to think outside the box and come up with novel solutions to engineering challenges. For instance, in the design of aircraft wings, engineers frequently use thought experiments to explore the effects of different wing shapes on aerodynamic performance. By mentally simulating the flow of air over different wing profiles, they can identify designs that minimize drag and maximize lift. This approach allows them to optimize the wing's performance for different flight conditions. Aurel Stodola's contributions span a wide range of fields, from thermodynamics and turbine design to technical cybernetics and the philosophy of technology. He was a true polymath, whose intellectual curiosity and innovative spirit led him to make significant contributions to both engineering and society. His enduring legacy lies not only in his technical achievements, but also in his thoughtful reflections on the role of technology in shaping the human future. He stands as a testament to the power of interdisciplinary thinking and the importance of considering the ethical and societal implications of technological advancements. His work encourages engineers to look beyond immediate technical challenges and consider the broader context in which their creations will operate. Stodola's work serves as a reminder that technology should serve humanity and that its development should be guided by principles of sustainability, equity, and social responsibility.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.